after the event. Okay, so what is data science? So let's think of our motivation for this IBM course and more for the MSc AI that you're going to go on to do. Okay. There's data everywhere. It's constantly being collected through smartphones, IoT or Internet of Things, sensors, Alexa, for instance, and contributed through Facebook and Twitter. Storage is cheap and compute power readily available and rapidly increasing. Computer clusters are available to enable parallelism, so being able to do multiple jobs at the same time, and special architectures developed for ML operations or machine learning operations. Okay. All this is available not just for those who can afford to own them, but through the commodity of the cloud. This increased ability to collect, store and process data has led to a revolution in how we do things in almost every field, from biological sciences to social sciences, humanity, political science, policy, marketing, and so on. So a whole range and breadth of the world. But just because we have the data doesn't imply we understand it. It must be processed to derive information, make models, enable predictions, and make diagnoses. We want to use the data to develop or augment models using machine learning and other algorithms. That's the essence of this course. So the key question in data science, how do we explain and predict things in the world? So the desire to make sense of the world is not new. In several domains, for instance physics, well-defined models have been developed which have for years been used to make predictions. The novelty in data science is the ability to create or refine models in domains where the underlying principles might not be understood. Okay. Now the basics of prediction tends to be simulation. So having a model for something we think happens in the real world, testing it out on a computer in a with controlled environments and the rules and systems, and then when it works in a simulation environment, taking it out to the real world. Okay. So we do things with testing and validation. Okay. We need to make sure we've got enough representative data to do any prediction though, and to be able to test that and ensure it's right and robust, and the right questions for good models. So the main topics, what is data science? Considerations around big data. What does analytics involve? Disclaimer and recap, and then checkpoint exercises, and there's a little notebook that we're going to be going through. So we've talked about what AI is, and I've given some overview there, but more than AI, let's think about just data science as a tangential but very related field. So if you were to do a word cloud for data science based upon terms online and in books and reports and things, you'd end up with something a bit like this here. If you've not seen a word cloud before, that's generally what they look like. The larger the font size, the more relevant and prevalent the words are. Machine learning is, of course, very important, as are statistical techniques. Languages, say Python and R, for instance, so you'll see Python is bigger than R, but R is an alternative programming language to Python. R is favored by statisticians, Python by computer programmers. Tools like Hadoop over here and Kafka over here. Databases like SQL, for instance, and then we've got MongoDB in there as well. Visualization, using things like Tableau, for instance, that's a fairly common visualization system, and then Power BI as well. The idea is that machine learning is part of a much bigger ecosystem and must be used at scale. We have to take account of all of these things as the applications and uses, for instance, of machine learning and what it relies on in terms of the data collection, storage, modeling, agglomeration, wrangling to get through Python to use our machine learning models. Now, data science is interdisciplinary by nature, and that's part of what allows us to convert into it, because it's by nature not a single disjoint area. So data science in and of itself is a mixture between computer science, statistics, and some mathematics generally. But the application of data science is then an intersection or a joining between this CS and stats and maths with science or economics or sociology or business or law or whatever area you're particularly looking at, education, finance. Okay, it just depends entirely on what the application domain is. So that was all missing in the word cloud because that doesn't show how inherently interdisciplinary data science is. Now, it requires domain experts to understand what and where the data is and how questions are important to ask. Mathematicians and statisticians to understand the modeling and inference, computer scientists to build systems and design algorithms and methods for analysis, visualization experts and storytellers to effectively communicate the results, and policy and legal experts to understand the broader social context. See the ethical implications of a field that has such a dramatic effect on every aspect of our lives, so getting a job evaluation, what ads are served up, etc. So data science takes ideas from computer science and maths and stats and applies them, that's the N or the intersection operator there, to these problems. So that healthcare example I showed earlier of the dashboard that I'd created and analysing the data set there, well, a lot of that was motivated what was required there and explained and the use of that by medical professionals. I worked very closely with consultants and doctors and experts in intensive care and anaesthetics and from all sorts of different areas, really a lot of cardiology experts as well. So I had to work very close with them to get a basic understanding of what was normal for those children and babies when I was trying to create an algorithm to try and identify abnormal behavior. Otherwise, what I would think would be abnormal, they would look at and go, well, that's just perfectly normal for that patient. So let's look at the difference between data science versus data analytics and data engineering. So we'll focus on the technical and data manipulation aspects of data science, which is often called data analytics. Okay. Some people also call it data engineering. Data science is far more broad though, and it includes domain expertise. It's not just about analysing and preparing the data, it requires you to understand what the application is involving, and they're communicating the results to users via storytelling and visualization, and accounting for some of the policy and legal implications and ethical issues too. Okay, we'll talk about data ethics, as I said, on Friday is the plan. Now, in data analytics, our focus is managing and creating models from data at scale. So complex, heterogeneous, large, high dimensionality, and velocity. When I say high dimensionality, I mean data that's got lots of different features about it. So if it was looking at shopping and marketing data, for instance, and I wanted to know about your shopping details, it may be that I've just got small, low dimensional information. So where you live and how much you spend. But maybe I'm a bit like Tesco and I've got high dimensional, lots of data and information there. So I know that you often shop on this day, that day, do this, buy that, buy these deals, are susceptible to marketing in this way, that way, don't drink alcohol. It's a range of different aspects there. So I'll focus on the foundations of machine learning cloud platforms, and you should continue to study these in depth afterwards. So this is a typical workflow for data analysis. We get raw data. Raw as in unprocessed, just collective. These are observations that are sampled from the world, whether it's come from all sorts of different sources, uses, information. Maybe there are two entirely different things that you're trying to see if they correlate and can merge together. What we want to do is then turn that into structured, integrated data. That's machine interpretable, and that's a general role of data analysts, trying to turn raw data into structured, integrated data. Then you can extract features, so measurable characteristics and useful things, like maybe one of the important features for that marketing data I was just talking about was where people live, and that's a relevant feature. Or maybe it's not. Maybe you don't care about where they live, you just care about what types of items they're buying in your shop. So get rid of that feature. Then you get into the modeling part and you go for the descriptive or inferential models of the population as a whole. So it could be in different systems or organizations, across different documents, databases, in different formats, for instance. Are there some information on websites, some in different databases, some in text documents, some from surveys? Do you join it together? How do you wrangle all of that data? Like I said, it can end up a bit like putting a tent back in the bag. So there are some serious considerations around big data. I'll talk about what that big actually means, right? But structure, cleaning, and linking as well. So there is this dichotomy that we've often got, especially in computing, between open and closed worlds, observations versus the universe, as it were. So databases often assume a closed world. We know everything, all of our data is in there, you can just manage that and deal with that. And that's often the computer science approach. And that's why AI is outside of that and moves more to the statistics approach, because we need to think that we don't have a representative sample of everything. So what happens at the fringes of that database of information, all the data that's been recorded? Have we surveyed enough people? What happens if the people that we haven't surveyed are entirely different groups? So data science is an open world. You can't see the whole population, often because you either can't get information for them, or if you were to go and collect it, you'd end up with so much information, you'd be dredging through that for years to come. So you're giving samples or incomplete observations and have to then generalize and do some subjective discrimination with AI. So if you want to predict the future or characterize the entire population, you're not going to have information from the future. You're going to have information from the past, and you're going to have to try and take that forwards. Now, sampling is one of the most important factors in determining the accuracy of results. It's a well-studied area that requires collaboration between the domain scientists and statisticians. In data science, however, data might be collected for one purpose and reused for other purposes, so there are additional issues of how representative the data is for a given research question. Okay, we'll briefly consider this later on. Facebook are often collecting and reusing data sets for different uses because they have access to so much data so easily, but they have well-formatted, structured data sets where they've gathered the information from millions upon millions upon millions of different status updates, observations, advertising information, backgrounds, trends, moods of people, how they've changed, and they've quantified those and characterized those, and then are using that data set for lots of different experiments. So once they've got that data that was really expensive to process, to manage, to wrangle, then they can do the data science experiments on that for lots of different outcomes. A famous one, which we'll look at in the ethics session on Friday, was about seeing if they could change the moods of users based upon showing them different adverts or different status updates and things. So show them more positive ones and see if that resulted in a more positive mood. Show them negative sentimental information and see if that changed their mood negatively. And they then tried to publish this results, which was, they got quite a bit of backlash for that from the academic community. So the SEC always likes to bring up this quote of past performance is not indicative of future results, often applied to finance, but in essence, you can sample everything up until now, but you're not guaranteed that that's going to be representative of the future. I think COVID has been a bit of an indicator of that. We can't predict everything. So I mentioned this concept of raw data. right? And then just sort of jump straight on. But let's have a look at this, raw data versus structured data. So raw data could be images like this picture of a cat, for instance. Who doesn't like a picture of a cat? Or genetic information, information about gene structure, or text. For instance, this text here, do not be like the cat who wanted a fish but was afraid to get his paws wet, by William Shakespeare. So that's text, that's data. There's not a lot we can do with that yet, though. We need to structure it to make sure that we can do something with it. So we need to bring it all together, wrangle it, and bring it into a form that can, for example, be used to develop a model for recognizing various types of cats. Okay, so we'll take all of this, tabulate it, check for any missing data, bad data, things that we need to take out of there, or descriptions that need to be inserted, to then format it into a structured system, and then we can analyze it properly. So the goal is to get raw data to structured data, so that we have fields, entries, objects, and machine learning features. It may be very regular or semi-structured. Ultimately, the goal is to go from data to information to knowledge. Okay? So if we're doing a cat facial recognition system, for instance, and we wanted to identify what different types of cats are, this is what the overlay of an AI algorithm might be doing to an image of a cat. But we've got different features that need to be recorded in our tabulated database and labeled. So we need to know where the cat's nose is. A human needs to go and put, a box around that nose to say that's the cat's nose, so that the AI algorithm can then go and learn that, so that when it looks at a new picture, it can generalize. Also the eyes, those are different features. The ears, the height of the ears, for instance. We've got a whole load of different features here. The origin, the coat, for instance, short or semi-long or long, and the pattern. If you're really into cats, maybe you'd want to go into different features that may be more relevant or more important to try and segment them. So ultimately, our goal is to go from data to information and knowledge. It's very easy talking about pictures of cats, and you think, well, that doesn't generalize very well. Well, it does, but trust me, we'll move on to a more realistic example. So linked data. So we've got information about people's activity online and their links and clusters and patterns, for instance. So we've got a person sat at the center of this graph, we'd call it. Not a graph like something that you plot, but a graph of information and connections between different activities or items or collections. So this person is linked to a friend here and another friend. They also watch Netflix and they cook this type of food and they like this game and listen to Spotify. Now this friend here is disjoint from those things, so they don't like this, listen to Spotify or cook those things. However, this isn't the only person they know that does cook that. There's a different path they can go along to get to that. So there could be a different friend here who they're closely or second-hand linked to that does cook that. Okay. Likewise, this person knows someone who listens to Spotify. They don't, but they might know someone else who does. What you want to then do is use Spotify targeting material and marketing point of view to try and expand the reach and get this person to get this person, this friend, to listen to Spotify, or this person here. So you want to expand the reach of these things from a marketing point of view. So we commonly represent relationships between entities or objects like these here on a graph, with nodes being the entities and edges being the relationships, so the lines between them being the relationships. Those are called edges in graph theory. You can then use the relationships to make the recommendations. Okay. There is an example of a Facebook graph, which is very complex actually, but if you want to download the slides and the links that I sent earlier on in today's session, then you can have a look at the notes and the links there. So if you've got data with more complex semantics, then you need to use things like knowledge graphs. So this has classes or subclasses or instances or properties where the nodes, rather than just being listening to Spotify or cooking this, the nodes might be documents that mention that person or were authored by that person, and then have a load of information that you need to try and understand from that document or this document here, and then try and join them together. I have a project that's just about to start, looking at water, floodwater proposals and things in the UK to try and use knowledge graphs and knowledge mining on those thousands upon thousands of text documents to understand what's been going on in that area in terms of flood management and proposals for avoiding water damage to properties, and then joining them together to come up with a recommendation system using AI for the best projects or which ones should be funded. We've got an example here of an educational organisation joining them together. So the thing is the organisation, which is an educational organisation. So the properties might be their URL or their web address. They've got the postal address or there's text in there, their aggregate rating, for instance, their rating based on a collection of reviews or ratings of an item, and their alumni. So a whole host of different information that could be encompassed in a graph and then modelled. Now, we can have an extra complexity in our data as well, and that can be temporal or time-bound. So data can be dynamic, high velocity, changing very quickly over time. You can track it over that time and try and then forecast what's going to happen in the future, but that's incredibly difficult. See, even with something like climate change, it's been very easy for people over a long number of years to say the global temperature has been increasing based on the data and will continue to increase based upon carbon output and all the various measures that they're using. What's not easy for them to do is to predict how that's going to impact the world, down to the area, down to specifics and the measures that can be taken to try and avoid those issues. So it's very easy to say naturally the world is warming, but where's it going to get most hot most quickly? What can be done? Do we have to migrate and move villages or towns because the layers of ozone above where they live is so weak that it's going to let through far too much sunlight and heat? Which towns and villages are those, and how can we do that? We need a lot more data, and then we need some big, usable, reliable AI to help that. So I mentioned tabular data earlier. So once we've got some data recorded, what we want is it in a table of some sort or a graph so that we can then clean it, model it, and learn from it, and then do some storytelling about it. So if we look, for instance, at this data that's been tabulated, we can see that there are column headings, a bit like an Excel spreadsheet or a database if you're familiar with databases. Number of passengers, how long the distance was that they went, where you picked them up, where they dropped them off. And from this you could infer what normal behaviour is for that taxi driver, and how far they were often taking people. What type, what groups of people got them the best lift? Is it better to pick up a couple or an individual? So you can reverse geocode data to get that. So you can get your location from this information or just from your phone. You can then find where they may have been going to and infer that someone's best business is in a certain area. And things like that can be obvious, but they can also sometimes be counterintuitive. So I've looked at some taxi data before where people believed that the best place to drop people off was at a shopping district, but actually restaurants tend to be the best place for picking people up after they'd had a nice meal, a nice environment, possibly some alcohol. They're far more willing to tip than those just going to a shopping centre, just going to spend money. What we've got then is a whole host of different information, so this longitude and latitude, and then we can use things like Geocoder and other online sources to try and see what's going on in that area. So join data up from one tabular database to then get extra information like Street View. So this is where someone's most often dropping them off. Even through Google Maps you can do this. So what makes data big? You may have heard of the term big data. Okay, does a gigabyte make data big data? So a DVD being 3 or 4 gigabytes, a Blu-ray DVD being 18 gigabytes, so quite big, high quality thing, or a petabyte, that's 1,000 times bigger than a gigabyte, or a yottabyte, so 100,000 times bigger than a gigabyte, or 1,000,000 records, or 1,000,000,000 records, or 1,000,000,000,000 records. What's big? How much information? So there's no consensus definition, right, on what is big data. Every different organization defines it differently, and it often comes down to compute power and human interpretability. So from our perspective, big data is always too complex for a human to understand it directly. Okay, you could look at it and try and see if there's any patterns or stuff going on there, but you're not guaranteed to understand what's going on in there. You're going to need to use some data analytics, some data exploration or exploratory data analysis to plot some graphs, get your brain to do some of the pattern processing and understanding what's going on there. Big data generally doesn't fit into a single uniform memory space. So you can't just create a variable in Python, and we'll talk about what a variable is very shortly. And it means we need to think carefully about on-off or communication between different sources. We need more than just what we call brute force algorithms to analyze things. So we can't just rely on an algorithm that tries to do something in lots of different ways. We need smart algorithms and smart systems. And that's why you need a bit of a background knowledge in lots of different areas of AI, so that instead of trying lots and lots of different models on solving a problem with data, then you can use one that you think should work to start with. It may require multiple computers working in parallel. Possibly lots and lots of different feature selection needs to be done to identify which features are more important than others. And it may be changing rapidly, so have a high velocity. So, final section, what does data analytics actually involve? So, it's a whole host of different things, but it generally falls into this idea of pattern detection. Going from data to knowledge or an action requires you to detect patterns in data. Raw data in, identify the patterns, give a partial understanding. And that's when the analytics ends and the science starts, because you need to merge that with domain experts to see what's actually going on and if that's realistic. Okay. So you perhaps show me sales by region, by product category, would be an analytics question that you can ask of data. That doesn't necessarily infer anything or tell you anything or what you need to do with that information. Show me clusters of documents by concept. So if you looked at an entire media company or a newspaper, for instance, if you looked at all of their different articles over the past 10 years and clustered them, what are most of the articles they write about? Are they a positive or a negative sentiment? Are they trying to stoke a culture war or not? Are they balanced or not? This is a question that's often asked about our national broadcaster, the BBC. And in lots of tests, actually, they show that the BBC, although it's often accused of being biased, isn't biased. In lots of tests, they've looked at documents and they give what they call fair or proportionate airtime to people of different opinions. So there's an argument that it could be biased in different ways, but just from a sheer amount of media time and representation that they give people, by clustering, you can show them that's not true. So typically we'll be doing descriptive statistics on data then. So get the data and run some standard, simple descriptive analysis to identify things like the mean, the median, the mode, the variance, all the stuff you may have heard of before if you've done any statistics. Then we can get toward the action part and the knowledge part. So given an observation, come up with a hypothesis, experiment over a sample, and then think of the significance. So for instance, hypothesize that behavioral factor F leads to the highest risk of outcome O. So more people doing this means this happens more often. So more people consuming more and more fast food leads to a higher risk of obesity. Collect some data, do statistical tests, measure the significance versus a null hypothesis. We'll talk about null hypotheses on the course, don't worry. But then you do a statistical test and then infer that your hypothesis might be correct with a 5% margin for error. And that's the important bit. What's that margin for error? Okay, and data science and statistics gives you a way of quantifying that. So, what does big data analytics involve? Acquisition or access, so getting a hold of the data, wrangling it, back to that tent again. Integration and representation, so our data relationships might not be captured, so we need to integrate them and join things together. Cleaning and filtering, it may have a varying level of quality. You need to either get rid of data or, like I had to with that healthcare data, fill in some of the blanks. Hypothesizing, querying, analyzing and modeling, so from data to information, and then go from understanding, iterating and exploring. That'll help you to build the knowledge. And then working with domain experts, you can then get to the next point where you want to be, to control the system. We also need to think about the ethical obligations always when there's data, when there's modeling, when there's stuff going on there. Okay? So you need to protect data, but follow good statistical practices and present results in a non-misleading way. Okay, and that's why we spend so much time on data visualization on this course, to try and give you those tools and techniques to give a robust and representative way of showing that data's information. So, we've got an example here of a Netflix recommendation, or it could be Amazon or a personalized search or something else. Right? So one of the first data science problems posed to the community at large from about a decade ago was called the Netflix Prize. Netflix wanted to improve video recommendations to their customers, and this is one of the cornerstones of their business model. Okay? So they shared anonymized data with the public and asked for solutions with a $1 million prize. And at that point, users would rate a movie from 1 to 5 stars. So every user from this database that Netflix had ranked movies from 1 to 5 stars. There's a huge amount of data available there then about what the films were, the information of them, and which people had watched which films and ranked them as well. So there's structured information about the movies, titles, actors, other people's ratings, text descriptions, and so on. Each person working on the challenge extracted different features, used them in various ways to make predictions using techniques from natural language processing over the text, machine learning, and a related technique called collaborative filtering. But the Netflix challenge ultimately revealed another issue that we always need to consider in data science space. It turned out that clever researchers were able to correlate the anonymous Netflix viewership information with reviews posted with IDs that were available online to the IMDb, or Internet Movie Database, that you may have heard of. They also reverse engineered who many of the viewers were. Now, it might not sound like such a data breach, but just think about it for a second. If someone managed to get hold of your whole viewing history that you thought was entirely private, based upon some IMDb reviews, and then going back through the data there, knowing exactly what you've watched, that could feel like a personal invasion.
Hi, Ian. Sorry that I could.
Okay, thanks. So we've got a question from Abdul. Perfect. Can we use quantum computers to understand large amounts of data and process them fast instead of using multiple computers? Theoretically, yes. So quantum computing lets you parallelize infinitely over lots and lots of operations, and providing that your search space is appropriate. So if your model is well defined, then yes, you can use quantum computers to work very quickly. The thing is, quantum computers are in their infancy. To be realistic, so we're still at the point where they're breaking into the field and they're not overly reliable. The main area that quantum computers are getting applied to is what we call prime number factorization. So sorry, it's a bit of a tangent, but it's worth going on. So if you take a number like 7, we know it's a prime number because you can't divide it by any number other than 1 and itself, and for it to be whole. So is 3, so is 5. But 4 isn't a prime number. Okay. Now, the way that banking works and encryption keys work really well is by joining together lots and lots of complicated prime numbers, and then using those to build a key to then unlock encrypted systems. Now, the idea behind quantum computing is that you can try as many different combinations as possible, almost infinitely parallelized, so that instead of going, right, if I'm going to look at the number 15, I need to check if 15 is divisible by everything up until 15 divided by 2. So 15 divided by 1, okay, that works, but that doesn't stop it being prime. 15 divided by 2 isn't a whole number, so it could be prime. 15 divided by 3, that divides into 5, so 15 isn't prime. So even just on a number like 15, you've tried 3 combinations. Imagine a number like 1,372,697. Is that a prime number? Well, a quantum computer would be able to factorize that in theory. At the moment, they've gotten as far as being able to try it on double-digit numbers. So we're well away from them being wildly useful. There's also a bit of a problem with the way that quantum computing works in what they call the entanglement stage. So the systems in quantum computing get joined together, and it would be very hard to know if you've got an AI algorithm that is entangled, whether or not it's truly solved the problem, or if almost like a mirror image of that has solved the problem, if you're into your computing background. So, or if a variant of that has solved the problem. So you wouldn't know robustly and reliably that it's definitely right, even if it's giving the right answers for what you think it's going on. So that's the problem with quantum, is just it could be in multiple different states at once, that superposition element. Okay? So it is a complicated area. Actually, last year, as one of the teaching sessions, not for the MSc AI, but I did teach about quantum chess, and that even just this simple game became very complicated very quickly using quantum mechanics. So I'll be happy to guest lecture on that. It's probably a Christmas one if people are interested. So just jumping back onto the Netflix side, in many ways, the Netflix challenge is a bit of a microcosm of the kinds of issues one encounters in data science. So techniques to extract the right features, techniques for machine learning, computing at very large scale, and being very cognizant of data privacy and other ethical issues are really challenging. So another example is high throughput gene sequencing. So genomics, this is the field of computational biology. It was an early example of data science. And about 10 years ago, they used to say that the best cutting edge developments in AI and data science were happening in genomics or at Google. Things have petered out a bit and have spread along lots of different places now, but about 10 years ago, those were the 2 places doing the best work, apparently. So genomics was an early example of data science, and it was putting the man on the moon grand challenge of the 1990s. See, over the decades, innovations in technologies to collect genomic information have provided a tremendous amount of data, and algorithms and techniques have been developed for its analysis. It was a precursor for what's now happening in many different fields across humanities, political science, economics, for instance. So high throughput gene sequencing, which has massive amounts of data, and you can't hold that on a single laptop or computer or even a couple of servers. You need to run that up in the cloud across hundreds of computers to do quickly. Things, it would have taken days to do gene sequencing in a physical computer stack or computing machine, whereas you can run it in less than hours now in the cloud. That's one of the Microsoft's adverts about that now. So the information also enables other things, such as personalized medicine, so developing treatment plans for individuals rather than a generic treatment plan. So working out genetically which systems and algorithms can then recommend the best medical interventions. So yes, you could be treated with medicine A or drug A, but actually drug B, C, or D would be far more suitable, quicker acting, or reliable for you with less side effects. So personalized medicine is reliant on this. So an example of the pipeline for its analysis is shown on here on the right hand side. Okay, so it is a rather complicated pipeline, but there's not a huge amount of moving parts in there once you've got the gene sequencing elements done as the data analytics goes, and a reliable machine learning algorithm in the middle. So data science requires human insight, in particular by the domain scientist. It's not just turning the crank and using statistics and machine learning and it'll always work the same every time. You need a different AI and data science approach to each different problem generally. And you've got to beware of overhyped expectations. And this is something that I try to make sure is quite clear to all the students on the course, that AI and deep learning and things get some great media time. Are they actually doing all the heavy lifting, all the hard work that everyone's being told they are? And are they really reliable or generalizable? So a data science myth is that we'll learn everything bottom up using fancy statistics and machine learning software. We'll turn the crank and pop out insights. Data and algorithms directly makes knowledge, but that's just a bit of a myth. Okay, data science reality is that we'll typically rely on human expertise to impose models over the data, the features, etc. And then deep learning or machine learning or AI can do feature selection. But why throw away what we know already? So data and human insight and algorithms plus iteration, so improving a model bit by bit, gives us information, which gives us knowledge. So data science application process. So when you're applying data science to a problem, first you need to think, what question are you answering? What's the right scope of the project? What data are you going to use? What techniques then are you going to try? We're very clear on try, not use or expect to work, but try. How will you evaluate your results and evaluate multiple different models? What maintenance will be required? Don't just assume that the world won't change based upon what your data and the modeling that you've done right now. So, final thing as a bit of a disclaimer. So, at least 80 to 90% of data science practitioners claim that their work involves no machine learning, but working with experts to understand an application domain, assumptions, and questions based on their background in data science and their understanding of AI. Trying to catalog and make sense of data sources, wrangling, extracting, and integrating the data, and then cleaning wrangled data. Now we're going to be doing a bit of this obviously throughout the course, but this is something that naturally you just build up with experience and get better at the more you do it. So it's going to be down to you really to build up your own experience. A bit like if you're going to the gym, you can try and lift a heavy weight and we'll show you how to lift a weight, but you've got to keep going regularly and lifting those weights to make sure that you're building muscle. See, data is high dimensional or has lots of features. This can be hard to understand and requires an understanding of computational costs. If you've got an integrated data set, and that's often the hard part, data science just involves extracting and selecting features as well as adding semantic structure to the data. And you can do anything with AI and data if you have access to the data. Okay, so that's the end of our presentation and the first Open Data Science for All presentation. So we've just covered what is data science and a bit of a general background and tried to give some of the distinction between analytics and the science. Okay. The next thing that we're going to be doing is going through this Colab notebook, so some of your first programming activities. Okay, can I just check, does anyone have any questions that you want to pop out now or ask before we get ready to move on? That's a very good question. Abdul, what's the actual meaning of semantic in terms of data science and AI? So semantic generally is the structured and relational aspects to make sure that it has a linkage and a relevance into it. So you want to make sure that you're collecting data that is semantic and related to each other and useful to each other, can be linked, joined, used concurrently. You don't want to be collecting lots and lots of things that you can't then join together. Okay, so it doesn't seem there's any other questions at the moment. So what we'll do, just conscious of time. So yeah, I think we'll take a 5-minute break, comfort break, because I've been going on for an hour about. So we'll do that, and then we'll come back at about 2:05, and then make a start on this notebook. Okay, let me just ping out the links to everyone for this. So the PowerPoint. So that's the link for Colab notebook. Here's the first set of files that include the presentation. And here's the second file that contains a larger file that we'll be working with later on, and I'll explain and introduce. Okay, this second set of links, the files, the first set of files, has all the presentations that I've gone through today, with the notes and things in there. If you haven't yet set yourself up with a Google account ready to use Google Colab, then go to those slides in the first set of presentations in there and get yourself going. Okay, so we'll be back in about 5 minutes. Hi everyone, sorry that was slightly longer than 5 minutes. I was just checking in, but it doesn't seem that we've had any questions from people regarding for the course or for anything that we've covered so far. So if you've got any questions, feel free, as I say, to ping those in the message chat or to raise your hand, unmute yourself and ask away. So can I just check, has anyone managed to access the collab file that I've got here from that link, that first link? Excellent, okay. Glad it's working. So this is a really broad and it's not overly basic, but it is a bit introductory use of Python. We teach Python using Google Colab often because of how easy it is to interpret, to use, to mess around with, and how we can create stuff and just share it out so easily. I'm just going to zoom right in so hopefully everyone can see. Let's check that people can see my screen in terms of this notebook. Perfect, thanks Prakash. So we're going to be going through this notebook, and ideally, if you're comfortable, I'd like you to almost go through it at the same time as me, and we could just talk through what each of these things are doing. We've got Yasmin still on the call, and I'm going to invite Yasmin to just jump in at any point if you can think of a different way of explaining what I'm doing in this code, given your experience over the past year and year and a bit of coming into programming a bit of fresh from an outside area, converting into the area, and to think actually, this is a better way of explaining that. So just feel free to jump in, Yasmin. So the first thing we need to do with programming when you're doing anything generally is type the words hello world. It's like a cardinal rule of teaching programming. You have to do it. So to run any code in Colab, we have to make sure that it's set up as a code section. Just going to clear on outputs. So just print hello world. So you can just click on the play arrow and it runs a piece of code. Now there are code sections and text sections. Text sections are stuff that I've written in as like notes almost, and then code sections are stuff that we want the actual Python coding to do for us. Now it may seem a bit silly in this, like printing hello world, but if we're printing out some values or some data, then it makes much more sense. Okay, so what if we want to do some simple mathematical operations? So 5 plus 0.5. Okay, so we can just hit run and it'll add that up and just come up with the answer, which is 5.5. Great, so that seems to be right. Word about multiplication. Well, you can't use an X because X is a letter. So in code programming, you use the star to denote times, a bit like you do in a calculator on the phone. So if we run that, we can see 276 times 52 is 14,352. Now, Python's great at working with data because it handles sets of observations. It can be done really simply using what we call a list. That's just a list of data stuff together. And lists are set up using square brackets. Okay, so if we've got a list of numbers, say 1, 2, 3, 4, 5, all we do is put square brackets around the edge and then a comma between those, and that will create a list. So if I hit play, it'll then print that out. And it may seem a bit silly, why are you getting it to print that out or hitting play on that? It'll make sense in a minute when we start using what we call variables. Now, variables are just that. They're things that vary. Okay. Now, that's not saved when we do this. Okay, and just print that out, that number. What we want to do is to save it into a variable, say x, so that we could do something with it later. And you may remember from school, or have some horrible memories or nightmares if you didn't enjoy the maths of it, with y equals ax plus b, or mx plus c, or equations and things like that going on. Okay, but variables are much more general than just solving maths. It's just something that we can store information in that we can then get out later, or modify or manipulate as and when we need it. So Python will save information into a variable, like x, but won't print it out anymore. So if I just delete this and hit x equals this, so this is a set of cars for the car company Jaguar. It's created this variable x, and it's got a list of some data in, but it won't print it out unless you print it out in some format. I could just print x, but that's just printing a list of cars. I know what those are, but if someone else picked this up later, they wouldn't know what they are. So I've just put this little statement, or this little text at the start, using these speech marks. So the cars are, and then print x. So if we do that, so cars are a Jaguar XE, an F-Pace, an XJ, or an F-Type. Okay. The great thing about Colab is you can edit code as you go along. So what if there's another type of car as well? So we can add in an extra one. So x.append, and we're going to append to it the E-type. Say that they've got this new car. Okay. Now again, it does things in order with code, so in programming. So first of all, we said what x was, then we printed it, then we've appended or stuck E-type onto the end. So if I want to see it with that E-type on, now I'll print it again. So it's x is this, got this data in this list. Then you're saying that the cars are the information in x. That's this first printed line. Then we're going to add an extra car, so the E-type. And then we're going to print it again. And we see this time it's printed it, but got the E-type on the end. So between this line and this line, we've got x, the variable with that data, and it's added in an extra one. So it's stored all that information and added this one. And that's where it gets really handy using variables. Okay, but for now I'm going to take these out. Now there's two ways we can get rid of stuff in Colab. You can delete it, or we can do what we call commenting out. So if you put a hashtag at the front of anything in Python, it just then doesn't run that line of code. It's what we call a comment. Almost like if you're writing a page of, or looking at a set of lecture notes, lecture slides, have them printed off and you write your own notes on the side. They're not on the PowerPoint slides, they're just notes for you. And that's what these comments are supposed to be. Okay, so all our cars, the variable x has XE, an F-Pace, XJ, and an F-Type. So that's really simple. What if we needed to use a variable to have calculations saved for return? So for instance, car prices. If we look at the prices first and then see what would happen if, for instance, in the UK, the Chancellor of the Exchequer decided to cut VAT on new cars. So cut the price of new cars by taking away the VAT, that's 20%. So to make that change, we'd need to adapt every value in the list. Okay. So I'm just going to get rid of all of this first of all and talk about what I'm doing here. In fact, I'll just shove a couple of lines different. So we've got the prices, and these correspond to these four cars. So the Jaguar XE, the car, costs £34,255. The F-Pace, £40,860. The XJ, 66,000 and a bit, and the F-Type, 54,000. So we've got cars in the variable x, and their prices are in this variable called prices. Okay, so hopefully that makes sense. So we can print out what the prices are. Yeah. So if I just get rid of this, Control X that, and then just play on this, then we'll see we're printing out what the prices are. Well, that's great. Perfect point, Yasmin. Yeah, so it's great and really useful to add comments in your code. So if I put in a comment here and just say, print out what the prices are, and then the actual code to do that. Now I've got some extra lines of code in here that is going to be entirely new to a lot of you, and don't panic. Okay, now this is a for loop, we call it. Okay, that last line is just printing the prices. So that's very similar to what this line does. Okay, so I'll put a new comment in there because we know what that does now. Print out what the new prices are. But we've got this for loop here, and I've just sort of thrown that in, a for loop. Well, a for loop says, look, you've got a list with these different prices in. We've got 4 prices here, and we need to modify each price individually. We need to make sure that they all reduce the VAT, so reduce the price by 20%. Okay, so the way to do that is, say, for every element or index in prices, the price of that car at that index is going to be prices, the current price divided by 1.2. I'm just going to run it so that you can get some appreciation of what it actually comes out with. Okay, so all it's done is gone, right, I'm going to look at the value 34,255 and divide that by 1.2 and shove that in there. Going to look at the value 40,860 and divide by 1.2, and that's 34,050, etc. So for same for the other two, and then it's printed out them. So I've modified the elements of the list in prices, or so each of those individual prices, and just divided them by 1.2, or taken away 20%. Okay, don't worry if you're not comfortable at all with this idea of a for loop. It takes a while. It took me a very long time, actually, from a mathematics and a business background to get comfortable with for loops, but they're not that scary when you're used to them. Now, that's how we deal with lists. But the thing is, we've got 2 different variables here. We've got X, which has the car names, and prices, which has the prices. But they're separate variables. We've got X and prices. Why don't we just have one variable or one item in the code that has both that information together, linked together? A bit like a database, but actually it's more basic than that. We're going to call this a dictionary. And like a dictionary on the bookshelf, if you've got one, it's got a key, so what the word is, and a value, like an explanation of that word. So dictionaries have these weird curly brackets, which you probably see on your keyboard. You might need to push Shift to get them up. Okay, so we're going to create an empty dictionary first, so just a dictionary with nothing in it, nothing in the middle. Now remember, when we created the prices, we created a list with lots of stuff in it, and you can append or insert new items to that. All we're going to do is create an empty dictionary and then start putting in the car name and the car price together. Join them together. Okay, so we're going to do that again with a loop. So for every element of the list prices, so all of these, we're going to say that the car name, or the name from the variable X, the price of that is just taken from the price variable, and then we'll print it out. And then we've got them linked together, so it's all tied up perfectly. So we can see that an XE costs 28,545 now, FPace 34,050. We don't have to look at X or prices, we've just got it all in this new dictionary called cars. Okay, and this kind of software, it seems really basic. You know, we've just done this in space of like 5-10 minutes. And this is the kind of software background that's sitting behind lots of car manufacturers, just with lots more types of cars and variations on what you can include in them. But the price of them, the charge for them and all that stuff, all sits on software like this. Now, we've got a dictionary, we can adapt individual prices and get specific information really easily. So if we wanted to look at the Jaguar XE and then cut the price of that by £500, say there was a promotion on that, how are we going to do that? Well, all we do is the value for the XE, the price of the XE in the dictionary cars is the current price, take away £500. So let's do that and print it again and see if it's done it. And then by magic, it's done it. So the XE was 28,545 before. Now it's £28,045. Okay. So that's two standard Python data types that I've very quickly covered. Lists with the square brackets and dictionaries with the curly brackets. Okay. So yeah, there's a great explanation on W3 scores, as Yasmin's pointed out there, and explains what a for loop is in Python, if you're not familiar. Okay. So far we've looked at two standard Python data types, lists and dictionaries. Now, we didn't have to use a for loop. We could use what we call an array, if you're familiar with that from computing, if you've done any before. But an array is a bit like a list, it's just a collection, or a bit like a column of data in Excel. Okay, and we can quite easily deal with that. So there's some code here to do what we've just done in a single block or single lines rather than using for loops. But we're not going to worry about that too much today. Okay, I'm just getting ready to move on to the next section. Now, does anyone have any questions what I've done with that list, the VAT thing or the dictionary? So I'll just put out a quick poll there just to see what the general feeling is for people. So great question there from Omemni. So a list just has a set of, or like a list of information, a collection there. Now a dictionary lets you have like a key or a title, a heading, and then a value to go with that. So we had to have two separate lists, one for the car names and one for the prices before. Whereas for a dictionary, we can say, here's the car name, and that's what its price is. Here's the car name, and that's what its price is.
Dictionary. They always come first. So you also see and then you value. I think that's right. So that's kind of like one of the main differences as well. If you ever get stuck between like a dictionary.
Yeah, thanks, Yasmin. So there's always a key and a value, whereas with a list, it's just a collection of stuff. Okay. So there's loads of great online resources for getting comfortable with some of these basic data types or common things in Python. Okay. And W3 Schools is one of the best for any sort of programming that you ever do. So we've got 14 responses on the little poll there, and it seems to be that people either get it or it's new, but it's okay. So that's great. Okay. So we've done a bit of work there. We're going to move on to an entirely new thing here, getting started with pandas. And pandas is one of the pinnacles of data science and Python. Now to do that, we need to use some data. So in that zip file that I gave you, the day1.zip, well, that's not right, is this Hubble data.csv. Okay. Now the only thing is it's not named correctly. In true academic fashion, I've set this up and then changed the name of the file. Not overly helpful. So I'm just going to run this and it's going to then explain. So we've got some data here, and this Hubble data is not very big. Generally speaking, you should always have a look at your data first when you've been given new data, just to see what's going on in there. And the easiest way is just to open that up in whatever readable format you can. So whether that's through Microsoft Excel or a notepad or, you know, anything really, just make sure that you can get it open and then see what's going on. Your brain's an incredibly powerful pattern processing device, so it would be ridiculous to not use that to its full potential. So this is what the Hubble data looks like. So it's data from the Hubble telescope, and I'll just zoom right in here. So it's the distance of things in terms of light years and their velocity or their speed that they're going. Either they're going forwards and it's positive, or they're going backwards and it's negative. Okay. So it's a data set with 24 observations, so hardly any data really, and it's got, you know, no missing data, but there's not much variation in distance and quite a bit of variation in recession velocity. So we need to be mindful of that. But all seems to be in order, all seems to be working. Okay. So we'll get that up on Colab. So I hit the upload button. If you'd unzipped the day one files, you'll found 1c_Hubble data.csv. So upload that. You'll need to change this line of code here, and it previously looked just like that. We need to say 1c.Hubble data, and it's going to use that. Now, this first line is importing pandas, so getting that set of algorithms and software bits ready for us to use from the pandas library. And then we're going to read in the data, and then we're just going to have a peek at the first few elements. That's what head does, data.head. So all of this data from that CSV file or from that Excel file that I just opened is all stored in this data variable now. And we've just looked at the first few here in Python. Now, you can view specific columns in the same way you do with a dictionary, and you can get summary statistics too. So you can look at the mean or the median if you're familiar with those. So first of all, print the distance. So this is all of the distances, but without the recession velocities. The mean distance is 0.911, and the median is 0.9. So that's some background information there. Okay. But that's quite useful to be able to do mean and median operations, and you'll want to do that when I give you the data set that you're going to be working on as a group. We can get Python to just do some summary statistics for us as well, which is brilliant. So it's looking at the data and says, well, for the distance column, there's 24 observations, and for the recession velocity, there's 24 observations. The mean value for the distances is 0.911, just like we saw, but also for the recession velocity, it's this. The standard deviation, or how much the mean varies, is 0.64 or 371. The minimum value is this. And the interquartile ranges, so the 25% value, the 50% value, the 75% value, and the maximum value. So it's just a bit of descriptive statistics or basic information about each of the different variables or the columns in our data set. Okay, what if we need to sort the data? Well, that's really easy as well. We can sort it by whatever column we want. Remember, we've got two columns, distance or recession velocity. So we can sort it by recession velocity. And then we can look at, instead of the head, where we looked at the head before and it was the first few elements, you can look at the tail end of the data set, or the last ones. Okay. Now, listing the data is okay, but often it's more useful to be able to plot what's going on and get your head into it and see what's going on. So we can see, if we plot, we get this recession velocity is this orange curve, and blue curve is distance. Now, you recall distance goes between 0 and 2. Recession velocity goes from -300 all the way up to 1,000. Right, so that's a much bigger range for recession velocity than for distance. So it's not overly useful, that plot. What we need is to be able to plot both of the variables there and see what's going on. So I've just got some code here, and all that's going to do is just plot two axes on there. So a y-axis here on the left and another y-axis on the right. So the red curve is for distance and the blue curve is for recession velocity as that goes up and down. Okay, we'll teach you far more things than this in the data visualization module, but it's just a simple way of plotting your data and seeing what's going on there. What we can see though in our heads is that as distance increases, recession velocity looks like it increases as well. So it seems that they both go upwards together. And that means they might be correlated. Now, there's a big argument for correlation versus causality, and that's something that we leave for the last parts of the MSc AI course, or even for people's projects. But we can see if they're correlated by importing a correlation function that someone's already created in Python and get that to do the work for us. So look at the correlation between distance column and the recession velocity column. Print that out, and the correlation, which is between -1 and 1, the correlation is 0.78 or about 0.8. So it's a really high correlation between distance and recession velocity. That's great. So we had a question in there for, instead of Colab, can we use RStudio and upload the CSV file over there and perform different operations? Yes, you can use RStudio and you can use R, Abdul. It's just a warning that the primary programming language on the course is Python, mostly because the things like the advanced image recognition and natural language processing algorithms already exist on Python and are very easy to import, rather than in R, where you have to do more work to prepare the data and get them ready. So, and Python is more the standard programming language expected for data scientists. But you absolutely can work in RStudio if you're comfortable there. So here's where it gets interesting. If the values are correlated, or if they move either upwards nicely like this, or if they went downwards like that together, that will be fine as well. Up and down, that would be okay. Or if they both go upwards together and they've got a high correlation, say 0.8 on a scale of -1 to 1, well, then we can do something with that. We can use some statistics or machine learning even to try and predict one value from the other, or predict recession velocity from distance. So if we have a measure of the distance of something, can we predict what its recession velocity, or how quickly it's going to be moving? Okay, so we're going to import or use this linRegress function in Python. And we know it's a function because when we say linRegress, we then put little brackets around the stuff inside the function. So we're going to use this linear regression function that's just going to try and come up with a way of predicting recession velocity from the distance. And then I'm going to print out some stuff. So it's going to print out the bits, the information about the linear regression, the stuff that we don't actually care about. So let's see how well it actually performed on 2 examples. So for the 10th data point, if we run that through our linear prediction, then it predicts that for the distance, the 10th element of distance, that the recession velocity would be 322. And in reality, it was 300, which is really quite close on a range from minus 300 to 1,000 for the current estimators. What about the 15th element of distance? Well, there it was slightly worse. So it predicted that the recession velocity would be 413 when actually it was 900. So it was predicting a much slower moving comet. Now maybe that doesn't matter. Maybe if that comet's flying towards you and it's going twice as fast as you think it is, that can matter though. So part of the problem is that it's not normalized the data. And this would normally be part of one of the data analytics pipeline pieces where they would scale the data, clean the data, make it all along the same work. So now when we've done some normalization, we call it, distance is between 0 and 1, and velocity is between 0 and 1. Now the data frame is normalized, and if you rerun the linear regression, then it looks much closer. Okay. Now, there is a section in this kind of notebook called Data Manipulation with Pandas, but based on the time and where we are, I'm going to just hide that and get ready to stop, actually, for this lab session. So there's some exercises that I've got for you here. They're not complicated in any way, and you don't have to do them if you don't want to, 100%. But if you want to see how well you've understood some of the stuff that we've done, then see if you can manipulate some of the data or some of the functions in code in different ways. So the first one is, instead of printing out hello world, can you print out hello world, I love AI? So that's this first line of code there. So change around what's inside here and hit play and see if you can get it to work. Okay, if you can do that, the second exercise is create a list with prices for a new iPhone, Pixel, Samsung, and an LG phone. Pick which phones they are. I don't mind if you want to go for an iPhone 12 or 11 or I don't know, what are they on now? 13, 21, something like that. So go for, put that in the variable X and put it in a prices list, and then see what happens when you remove, rather than tax, the VAT at 20%, what happens when you remove import tax at 12.5%. So that's doing exactly what we did up here, where we took the cars and we changed the price of them, but instead of divided by 1.2 to remove 20%, take away 12.5%. Okay, see if you can do that. And then if you're feeling adventurous and want to give it a try, for the Hubble telescope experiment, see if you can swap around these variables, and instead of using distance to predict recession velocity, swap it round and use recession velocity to predict distance, and see if it's any better at prediction for these 2 examples. Okay, you can either edit the code in there, or you can copy it and paste it down here. So we could copy it and paste it in here, and then you can start to edit and swap around recession velocity and distance and see what the results look like, and then hit play. Okay. So there's a few exercises for you to go there. But as far as today's activity is done, I think we're coming to a close there in terms of the CoLab notebook. Yeah, Abdul, that's it. We're going for making sure that everyone's really comfortable with what we've done, where we are, and giving that a try. And something as simple as switching the variables may seem like it's really easy or trivial, actually isn't, can require a bit more work. But the thing with coding is, most of the code and the problems that you'll ever hit with programming, especially from an AI front, have already been done or solved by someone else. So there's no point in you writing a 1,000 line notebook of code from scratch. You might as well look online and go, right, someone's already, if I'm doing an image recognition algorithm or facial recognition, well, there's a great facial recognition algorithm I can use that I can download from this place. Then I can train it on this data and I can use it in this way. And all you have to do is write a few lines of code yourself to stitch things together. But as Yasmin will be able to attest to, lots of the stuff is already online, and code solutions are online on Stack Overflow, or just there's great guides online for how to do certain aspects. So even by the end of the course, you don't need to write that much code yourself from scratch. You need to go away and see how other people have solved similar problems and be able to blend their code in with yours. Just be able to check that it's working. So, and I would suggest using this Google Colab. So sign into Colab using the information in the slides that I shared at the beginning and that people have sent the links for a few times. And then you can be able to go to this Colab notebook and run it this way. If you want to do it locally on your computer, then you can use Jupyter to do a Jupyter notebook. It's up to you. Or you can just download and use the Python code and do it in Spider. So those are two popular ways. Spider is generally the one to do it on your computer. Okay, you might need to download the Anaconda library to get it all working. Yeah, there's some great resources on YouTube. Absolutely, thanks Yasmin for that. So what I'd suggest is, if you're feeling comfortable and want to give it a try, and I really would recommend going for it, have a go at doing these 4 things. Okay, and then there's one last thing that I'm going to recommend to you all as well. So as we come to a close, there's a link here to a video that I'm just going to go and put in the chat. Okay, so I'll just pause it there, and I'll paste that in the chat there. So this is a YouTube video. It's an hour-long video, but it's by Armin Pistoshian, one of the brilliant researchers at IBM, who was part of the Watson group actually, that was on the Jeopardy thing. So it was one of the first big advancements of AI in the real world that got people on side. Right? So it's a great video of him talking about the landscape of AI in quite an approachable way. So if you're having dinner tonight and you want to put something on, or if you want to dedicate an hour, it's really good to just give you an understanding of the scope and scale, to round out some of those things I talked about earlier in terms of narrow and general and artificial superintelligence. He's talking about some of the more practical aspects, okay? But it's just really great for you to immerse yourself in AI, what AI is, what different people say about it and do about it and things, okay? So the recommendations, have a go at these and have a watch of this video, okay? Now, I've not had any more emails come in with questions in particular for me to go through in terms of that Ask Me Anything, but I do want to dedicate a bit of time just in case anyone's got any questions right now for me. So to let me, if I get the share link, copy that. So to you should be able to click that and go onto it. But if you can't, it'll be because you're not logged into Google Colab. So if that's the case, then what you need to do is set yourself up on Colab. So the easiest, I'll just run through very quickly how to do that. So if you go on Google and search for Google Colab, the first link that crops up will be Google Colab. So click on that. It'll take you to this page and you need to click sign in over the top right. Then if you haven't got your Chrome browser, which is the best one to use for this, signed in with a Google account, either if you've got a Gmail or another email address you want to use, click create account. It asks you for a first name, last name, and it suggested Gmail, but you can use my current email address instead. So if you click that and then fill in your information, and I filled it in looking like this, so I clicked that and then I said my first name, last name, email address, and I use my bcu.ac.uk email address, and then put in the password and confirm. Hit next. It asks you for a phone number, your date of birth, and your gender. Hit next. Accept the privacy terms by scrolling down, confirm. Then you're signed in, and you can either click on that link to access and run the Google Colab thing, or you can download the files that I'd given from the link that I'm just about to paste again, and then you can hit upload and upload the .ipynb file and then run it. So the actual files can be found here. Okay, so Abdul, you asked about can we really build chatbots using IBM Watson in less time? Yes. I don't know, Yasmin, if you're comfortable, do you want to talk about, you mention briefly what you're doing on your project? Just a few lines.
Yeah, I can speak. So with my project, for my master's project, I'm doing a placement with a company called Meganexus, and they kind of want me and another student to build a chatbot. It's our first time either of us even using any chatbots or anything. But Rasa is a really good online platform to kind of build the chatbot. And just quickly, that the most important thing about when you're building a chatbot is to train the algorithm, especially something called natural language understanding. So this just ensures that the chatbot is able to communicate with the user really well. So if the user asks a question, for example, like, do you have this shoe in a size 2? The chatbot can recognize, what the user's asking for, and then they can send, the useful information. So they'd be like, yes, this is in stock, or no, this is not in stock. So you do learn natural language processing during this course. So you learn kind of how you build and train the algorithm. So that's briefly what I'm kind of doing right now. Everything's kind of learning by doing. As I said before, like me and Jess, we never really used chatbots before, but we just use everything is online. Lots of documentations online, lots of YouTube videos are online. So I think whenever you're stuck, even from like you're doing like a master's project or you're doing like a little bit of code for university work, there's so much stuff online. So don't be scared or anything, because even now, like it's coming to the end of the course and I'm still learning everything, still learning like new things all the time. So yeah, just don't worry if you feel stuck, especially right now, because it's like your first time, being introduced into coding. It took me ages just to do like Ian said, like a for loop, but even now I'm still like, oh, what is that again? So it's just lots of practicing, and yeah, just practice makes perfect. So yeah.
That's great, thanks Yasmin. So absolutely, I'd reiterate that point. So although we teach you how to do things along each of these modules, you get experience in stuff and hands-on wherever possible. The project is really where you come to shine, and you've got your own self-direction. Yes, you have a supervisor, but you're meeting once a week, and the project is down to you. And so Yasmin and just they're working with a company who are almost biting at their heels, saying, right, we need to do this. This is the project, and you're going to produce this for us. And that's the great bit, in terms of experience. But that's where they're learning things very quickly on the job. And this is what shapes the rest of your career as the master's project. And these are the things that people talk about as you go along, into careers going forwards. So just before we draw to a close, I just thought it would be worth framing what we've covered today briefly, and then where we're going on tomorrow. So we had our introduction to BCU briefly. We had talk about the MSc AI, the course, and the position of AI in the world, and thinking about AI for good. We've also then moved on from that to talk about the basics of data, Python, and information, and looked at the difference between data analytics and data science and some of those aspects. And you've done some of your first Python programming, hopefully. We went through that Colab notebook, which everyone has access to. So, and I'll set you a few simple exercises to do. If you struggle with them, don't worry though, okay? It'll be because you're doing something entirely new. I wouldn't expect to be able to go abseiling and be able to do it all on day one, even if I'd watch someone do it. Okay, even if they tied the rope for me, it's still walking off the edge. So I wouldn't feel overly comfortable with. And I imagine that if you're doing this for the first time, you might not feel comfortable with that, and that's okay. But this is just there for you to do in your own time. Give it a try. If you get stuck with it, ping me a message, privately an email, or say in tomorrow's session, Ian, I tried this, but I wasn't sure if I got it right. Can you just show me how you do it? And of course, I'll do it. Okay. So that's where we've covered today. And we've talked a lot about different aspects of the course and projects and things. Tomorrow, we're going to be doing the open data science for all, data cleaning and wrangling, and modeling data types and algorithms. So we've got 2 big workbooks to work through from there. And again, there'll be plenty of opportunity for you to ask me anything in terms of BCU, the course, or AI in general. Again, just ping me a message through my email, and so I'll just make sure that everyone's got that. We really need to have this just copy and pasted. So ian.rice@bcu.ac.uk, and make sure that you have the subject line question, because obviously it's quite a busy time of year with marking and things. So I'm getting a lot of emails coming in, and I want to make sure I answer your questions or record those as a priority for this week. So if it starts with question in the subject and then what the question is, I'll make sure that I talk about it, and I'll treat it anonymously. So thanks everyone for your time today. I'm making sure that these recordings are going to be available to you. So I'll be saving these as they finish and close, and then I'll get them online onto a YouTube account, and then ping out the links to everyone in the email following up from today's session. Okay. So thanks very much, everyone. I'll be calling the session to a close there. Did I see? I think I just saw a hand go up. I'll just stop the recording.